Hello everybody. Today I'll be presenting a presentation on the Monte Carlo by Ising method as my presentation. So briefly, before I start, I want to give you guys some quick background on some context information you should know so you're not confused during this presentation. One of them is the Monte Carlo. So what is a Monte Carlo? It's pretty much a goal to estimate the possible outcome of a range of values rather than find the input values and create possible distribution via histogram. So the key thing to remember is possible outcomes. The Ising model determines phase transitions in thermodynamic systems. It relies on the magnetic dipole moment of atomic spin, the use of magnetic vectors from the electrons rotating around the nucleus. Key thing to remember is it uses magnetic dipole. Or you could also say it's magnetism. The metropolis algorithm is an algorithm that defines all conditions in order to calculate the microstates that the molecule will undergo. The important thing to remember is it defines the conditions. The goal is to use a Monte Carlo approach with the Ising model that can help understand how potential values affect phase transitions by metropolis algorithm to set up a 2D model of spins. So there are a couple of methods. The first one is the Hamiltonian. Then we have to incorporate energy, magnetization, and the metropolis algorithm. So the Hamiltonian is used to account for the neighbors' lattice sites that will be projected in the system. The C and the D are those neighboring sites. As far as energy, the only thing we're doing now is we're using what's called the ferromagnet total energy equation in order to compensate the Hamiltonian along with, I guess you can say, the algorithm, to incorporate in the algorithm so that we can calculate in the future. But pretty much the important takeaway of this is that it assumes that there is no external magnetic field, gives it a condition. And the J is just a regular constant. For magnetation, this equation will be used. Pretty much the M is the net magnetic per volume, and the N in the equation is the total number of spins. So the metropolis algorithm, sorry, typo, but so pretty much it's this equation right here. So the theory behind this system is that one can assume that a system can reach a specific condition, which is given as alpha, at a given time if the way is defined by the possibility of finding this system at a given state. Given our system a chance to obtain equilibrium, this equilibrium state will allow for one to use the Boltzmann distribution to find alpha and therefore predict a value, which we'll define as foxtrot, and that has a possibility of being at the expected state given the following equation that we just see on the screen. And then to incorporate that in the algorithm itself, we will use this equation that will use the Boltzmann distribution to make it possible. However, these exact equations cannot be directly incorporated in MATLAB, so they were manipulated in a way where it actually worked out because it kept getting errors. But on the bright side, for the 2D Monte Carlo, we got it. So pretty much the ferromagnetism, pretty much illustrated in the picture, gives this pictures of Rubik's Cube similarities. So pretty much it shows that the ideal temperature is 5. Keep in mind that the 5 is in kilotemp, is like KT. For magnetic susceptibility with an elapsed time of 0.13557, which that is incorporated in my paper, but this is a general information. The evaluation was given for 7 spin sites per side with an exchange of 2 over a Monte Carlo simulation, and also was used in a sweep to get the most accurate representation of that 2D graph. In order to see exactly how temperature was affected and played a part of this, I plotted it in this graph right here, and pretty much you can see that how the energy varies a lot when you apply the energy and you compare that to the temperature. You can see it gets much drastic, as the red lines indicate. On top of that, because of the Monte Carlo, I also made this, which pretty much shows how the magnetism is affected in energy via a frequency. It's not perfect. It's not what I wanted to get, but we can see what happened. And this figure here, it just pretty much shows the distribution of how it worked. In conclusion, the simulation creating the 2D model was successful. Temperature does affect spin. There could be further research and improvements, but it's important thing to remember is that a Monte Carlo via ice model can illustrate and predict how molecules will behave if the temperature is changed. The combination has allowed phase transition of molecules because it goes beyond the one dimension where Ising model is restricted. It shows that higher T values, the spin tends to be randomly aligned, leading to a zero average. Magnetization, thus lowering T, will be more predictable with the spin alignment due to the magnetization being zero. And in that presentation, or in this Rubik's figure, you will see that if we decrease the temperature, let's say to 1, there will be a far more yellow because it's more stable. And the more chaos it becomes, the more little cubes, squares. Pretty much, I may have forgot to say, but the yellow represents an upspin, purple downspin. So back where we're at. So this result can conclude that the traditional will favor ground states and are more visible in the two-dimensional metal, with fewer colored patterns because the spin are more balanced at lower temperature. As I stated, this model can be applied for greater parameters and applications like showing these behaviors in a 3-dimension model, and it's something worth looking into, which hence the further research and improvement. Again, another way to improve my graphs, which I have seen in some papers, is where they actually do a simulation where it actually moves around and you can see the transitions moving around. That was too advanced for me, but it's something that it can be done if you understand and give a more defined algorithm. And that's my presentation. Here are my citations. If you guys are interested, check it out. You can check it out here. More information. Thank you.